Matthew Romney. He's my teacher last year in 322, analysis in several dimensions, also an independent study we did, and we did also a project over the summer in geometry of surfaces. So yeah, I'll just let him do the talking now.
Well, thank you for that introduction. So I want to talk a little bit about my own research interest today. And as Adam alluded to, it became the basis of an RU project for the summer, which I'll kind of allude to, but maybe just focus more on just the topic in broader terms. So I put down as a meta topic, doing mathematical research, because I thought, well, how can I make this as meaningful as possible? And maybe you don't care about surfaces specifically, but I bet as many of you have thought about doing mathematical research, either as a professor or just in grad school, or maybe even currently, for like a thesis or some kind of capstone project. So maybe research is on your mind. And so I thought I'll kind of approach the topic from that angle with the hope that something will be valuable. Okay? But at least I'll talk about what's helped me, and then if it's helped me, then maybe there's a chance it'll be helpful for other people as well. So to state with the obvious, I think the first step is to just have a topic. Okay, you can't do research without a topic. But I think the key thing is to make it both specific enough to make progress, but then also broad enough or deep enough that it can really sustain serious research without you exhausting it. Okay, so it should be kind of open-ended to some degree. So you might ask, first, on a personal level, what do you find interesting? What do you find meaningful? There's maybe a math topic it just might seem kind of arbitrary to you, and you don't see the meaning in it, and that's fine. Look for something that you do think is interesting. And I think the second consideration is what is not well understood by the math community generally that you think ought to be. Okay, what is not done? What is the gaps that are out there, and have that be your guide. So for us, we're kind of given the topic, and we're talking about surfaces, and from the point of view of metric geometry, right? Because the surface, you can think of it topologically, but that makes it, I think, fairly boring, at least well understood. Because there's a topological classification of surfaces, but that's been around for 150 years or so. But then from the point of view of geometry, well, maybe there's more to be said. Okay? So then I put a step number 2. What you can think about is what are the relevant or interesting examples. We can say the guiding examples. My own opinion is if you don't have a rich source of examples, you're kind of just doing mathematics in a vacuum. Okay, it's like the adage of it. If a tree falls in the forest, we can hear it, does it make a sound? And if you prove a theorem, but you don't know what it applies to, then does it really count as a theorem? So I think you need to have a good source of examples, and that, together with the theory, is what creates meaning and creates interest. So you might think for surfaces, what examples do we have? And as a first step, you might start with extremes. So one extreme being the most trivial you can think of. And then on the other end, what's the most complicated, exotic, pathological, bizarre object you can come up with? Or maybe the most general type of object you can think of. So that would be the other end. So the trivial versus, so either exotic, extreme, or maybe just very, very general. Extreme is maybe a redundant word to put here, so we'll put just either very exotic or very, very general. So for surfaces, what do we have? So I'll come over here and I'll put, I guess, the mathematical content on this part of the board. Okay, hopefully it won't hurt the camera too much. So probably the simplest ones you can think of would be just the Euclidean plane itself. Okay, that's kind of the first surface we encounter, to the point that we don't really think of it as a surface necessarily, just as the plane itself. Perhaps next after that would be the sphere, the two-sphere. The hyperbolic plane. Okay, so these are the three geometries of constant curvature. Okay, and that's probably the most simple we can think of. And so then we could ask, what is the next step after this? And I think the next level would be, well, I guess two options. We could either say polyhedral surfaces. So these would be surfaces formed by taking pieces of the first type and then just cutting them, pasting them, gluing them together to form something a little bit more complicated, but probably not that much more complicated because it's still the same fundamental building piece. So polyhedral surfaces, maybe just a quick picture to supplement this. So something like that, where you're just taking polygons, maybe just triangles even, gluing them together. And really the only complicated thing would be these vertices where you have maybe some type of metric behavior at the vertex. So it could be maybe positive curvature, negative curvature. So parallel with this would be smooth surfaces, or we could say smooth Riemannian surfaces. And so just for reference, how many of you have taken the course, like differential geometry of surfaces? Nobody here? Okay, it's one of them. It's one of these electives in the catalog. So I think some people may take it, but it's not essential, I guess. But yeah, there you're looking at the differential geometry of surfaces, and everything's in the smooth setting. A surface given by some type of formula, typically. So often in R3, where you have some kind of function from the plane into R3 that gives a surface, and then you have some smoothness on everything. Or you can think intrinsically, where you define a surface by specifying a Riemannian metric, so which was an inner product at each point. we think of surfaces from a classical point of view, we're probably thinking of this setting here. Okay, everything's smooth, just to make it as clean as possible so we can focus on the fundamental concepts of curvature, Gaussian curvature, and different variants of that. And then using that to build the theory of surfaces. So any questions at this point? So feel free to ask if there's anything as we go on that either want more explanation or just to hear more about. Okay. Yeah, so I think I'll draw a continuum here. So on the one end we'll put trivial, on the other end we'll put so either the most general or the most exotic. And so within this continuum we probably put like R2 right there at the left end, and then we could put smoother polyhedral. So at the very, very opposite, we just have an arbitrary topological surface with some metric with no further assumptions, except that the metric should be continuous so that it actually is compatible with the topology. So we can think of these two extremes, right? We have what's either trivial or at least well understood on the one hand, and then to make some kind of statement or claim about an arbitrary surface is probably impossible. It's probably too general to really make any kind of meaningful study. So then we can ask, what is the middle ground in between? Because where do we have enough structure to make a study meaningful, but then not so much that we're back to the trivial case. And I think that's kind of the essence of research, is to find this middle ground. And just do like an explore within it, to just uncover something that hasn't been uncovered. So actually, before going on to the next topic, let's discuss examples a bit more. So I'll add a sub point here, which is to think in terms of construction. So if we want to give an example of a surface, what would be kind of the natural scheme to produce this kind of example? And for surfaces, there are really two possibilities that come to mind for me. So one would be to build a surface as a subset of some kind of ambient space. So perhaps R3, or it could be something different depending on what we're after. So a subset of R3 or another ambient space. And if you like fractals, this, it goes hand in hand with this. Because when we talk about building a surface, there might be some kind of iterative rule that we use. So how about begin with a cube? Or I should say the the boundary of the cube. All right. So maybe take that as the initial surface, and then well, how about just delete a portion of the face, add something in, so add another cube, do the same kind of thing. And then just repeat this. Repeat it infinitely, and then you're going to get a bit too much to draw meaningfully with it. So you can just imagine doing some kind of replacement rule, do it infinitely times, and you get some kind of limiting object or fractal object, and it's a surface, a perfect good surface. You give it a metric, so either just give it the metric from R3, or if you want to, you can give it the intrinsic metric, where you measure distance just by the shortest path from one point to another. So this kind of object, you might call it a snow sphere. Just an analogy to, you might know the on-box snowflake, which is a curve in R2. We're doing a similar type of thing, but just with the surface in R3. So we could call it a snow sphere. Yeah, and in that case, just an example to think about. Okay, not terribly complicated, but it does show that you can't have, say, fractal behavior. You can't have, in this case, the area is not going to be finite. So when we talk about surfaces, we can't rely on, say, a property of the area being finite unless we impose it as an assumption. Yeah, so then the next possibility is to think of defining a surface by beginning with, say the plane, and then just weighting it. Okay, so you just change the metric by, say take a function, or some variation on that to just modify the planar metric by weighting it. So in this connection, there's a theorem called Moore's theorem. I don't know how familiar it would be. Has anybody heard of it before? Just out of curiosity. Except maybe Adam, just because you're the researcher. So let me just paraphrase it. I don't want to necessarily give a precise statement. If partition plane into non-separating continua, and take the topological quotient another assumption about upper semi-continuity that I don't want to get too much into. Let me just finish the line first. The resulting space is homeomorphic to the plane itself. Yeah, so let me just add here. satisfying upper semi-continuity. So just to illustrate this with an example, so you can take just a single continuum. So how about the disk, the closed disk? We just say non-separating, because we can't take a circle, just that has to be. It has to be something that contracts to a point, for example. And then we form a topological space just by contracting this to, or shrinking this to a point. Just imagine the space that way. It's, a priori a different topological space, but you can show that it actually still is just a plane from a topological point of view. But this works basically no matter how you do this. So you could take say multiple line segments, okay, collapsing the points topologically, you still have a plane. All right. What this tells us from a metric point of view is that you can use this idea to construct different spaces that are still topologically surfaces. Okay. And you can think of it essentially as here in this case, defining a weight, so we'll call it f. So f of x is, if this is the disk, we'll say the closed disk, the indicator function of R2 minus the disk, and then length curve. So how about gamma to denote the curve is the integral. So think of a path integral of the function f ds. Okay, so that just meant to be a little bit more of a rigorous statement of this. So we're constructing a metric space where we take the disk, just collapse to a point, and then maintain the Euclidean metric elsewhere. So it's a perfect big surface, homomorphic to the plane, and it just has this different metric feature where if you want to travel from, say, from here to there, the quickest way is to walk towards this hole here, and then pop out there on the other end. Then that becomes the shortest path. So if we're thinking in terms of geodesics or shortest path between points, they kind of all get attracted into this this hole, and then they can kind of travel arbitrarily at that point and then connect to other points. Okay, let's take a moment for questions. I'm looking at the clock, so we have about another 10 minutes, I think. So let's move on to point number 3. So what has already been done on the topic? So if you want to make a contribution, then it seems natural that one of the first steps should be to really figure out what other people have done. But in part just because this is the most reliable way to produce work, right? Because if you can find something of value in what they do, you can just extend it, and then that already has become a research project. You don't have to reinvent the wheel every time, but just take what's been done and continue to work with it. how about I'll erase this part here. So we might ask for surfaces, what is the important prior work that we should be building on? And we alluded to the just the classical differential geometry of surfaces. One aspect of that I want to point out is the classical uniformization theorem. This is something that's often covered in a complex analysis course. It states that any smooth Riemannian surface is conformally equivalent to a surface of constant curvature. And it's a very strong result. It's one of the, I say, the great achievements of 19th century mathematics. And one way to think about it is it kind of connects this second level here back to the first one. So you get from R2 to STU, so R2 slash S2 slash H2, right? These are the three model constant curvature surfaces. So these are obtained from the first level just by some conformal change. Okay, we can think of these as being conformal deformations of these three model surfaces. Okay, there's a little topology you have to account for, and that gets into cover spaces and that sort of thing, but I think the idea itself is pretty simple. Now, the next piece of prior work I want to talk about is what's called the theory of surfaces of bounded curvature, or we say bounded integral curvature. So if we ask, what is the next natural level after the smoother polyhedral category? So historically, this is, to my knowledge, the main answer. So beginning in the 1930s, there's a Russian geometer by the name of Alexandrov. He came out of the scene and improved a lot of stuff with specialized surfaces. And today there's a branch of geometry called Alexandrov geometry in his honor. And one of the fruits of that school is what's called the surfaces of bounded integral curvature. Or more precisely, we could say BIC surfaces. And it's kind of an immediate generalization of Riemannian surfaces, where instead of defining curvature just by a formula, you define curvature in a more intrinsic way, and that's done by comparison with by comparison with model triangles from the class of constant curvature surfaces. So I don't want to spend too much time just to keep on moving, but I want to point out maybe some highlights of this. So we can think of this as being the most general class of surfaces for which curvature is a geometrically meaningful concept. In the sense that in Riemannian geometry, if you know the curvature at each point of a surface, then that essentially determines the surface. Okay? You ask, like, what's the largest class of spaces where if you begin with curvature, that's some kind of measure, like a sine measure on the end of my space. You can take that and recover the metric. We get this class of surfaces of matter and curvature. And you might think of it as being like Riemannian geometry, but allowing some kind of non-smoothness or singularities. So we'll put that as the next step in our hierarchy. My other comment related to this topic is that the main method of Alexander himself is polyhedral approximation. And this segues into sort of the next bullet here. And that is to ask questions. To ask questions fearlessly. Okay, they might be stupid questions, they might be naive, but that's okay, as long as you don't expect to have a perfect answer every time. So for an analyst, so such as myself, if we're thinking like, what's a typical question schema we could follow, that would be, how do you build complicated objects out of something simpler? Okay, you think of the theory of integration. How does that work? You define the integral first of a simple function that only takes finite values, and then kind of by approximation, then you would eventually extend that definition to arbitrary measurable functions. So this kind of idea is sort of the scheme of analysis, to look at simple objects, put them together, do something complicated. So we'd like to think of taking limits of simple objects. And here you could ask, okay, what's the sort of the fundamental building block of a surface? Well, this takes us back to the idea of polyhedral surfaces. Just think of triangles or polygons. Just glue them together, and that's sort of the obvious way to build a surface out of elementary pieces. now the question becomes, okay, what surfaces do we get as limits of polyhedral surfaces in some kind of nice way? All right, and that takes us to a bit of my work on the topic. So I began working on surfaces kind of in this context of Alexander geometry. So beginning with surfaces of uniform curvature, and following a suggestion of my mentor, we asked, okay, can we sort of take this theory here and remove curvature from it and still be able to get the thing to work? Okay, and what generally would that be? So for our work initially, we assume just you have a length metric, meaning that if you take the distance between 2 points, this is given by the length of the shortest path between them. So note that the distance function of your surface corresponds exactly to lengths of paths between points. So that's called a length metric, or also called an intrinsic metric. And just based upon that assumption, that's enough to kind of get this whole polyhedral approximation thing off the ground. So again, an arbitrary surface with a length metric is the limit of polyhedral surfaces in a nice way. And we can do that, again, without sort of these traditional assumptions, really just relying on having a length metric. And then an application of this is that we have another assumption. If the surface has locally finite area, we can prove a version of the uniformization theorem. Uniformization and it takes a bit of work maybe to find the right statement because this conformal equivalence is too strong. But what we show is that if you relax it to quasi-conformality instead of conformality, so you allow some kind of distortion but in a controlled way, and then if you allow collapsing, then you still get a nice parameterization of an arbitrary surface. And so there's a whole literature behind to these uniformization theorems, and so we'll expound on that and contribute something to it. But I think to say more would kind of get us a bit technical and kind of beyond the scope of the talk. So I think this is a good spot to end. So we'll turn it over to any questions if you have any.